Welcome back to the deep dive. Have you ever scrolled past headlines about AI and thought, what's really going on inside these systems? Terms like machine learning or generative AI get thrown around constantly, but truly understanding their inner workings can feel, well, like trying to decipher a secret language. Today we're taking a shortcut, a true deep dive, into a really robust and enlightening source, the ISICA Advanced in AI Audit Official Review Manual. Now, okay, while this manual is designed for auditing professionals, we're going to use it as our expert guide to unravel the very foundations of AI models themselves. We're specifically pulling out the key insights from its Chapter 1, Part A. Our mission today isn't just about defining terms, no, it's to demystify the core components of artificial intelligence. From the most basic types all the way to the intricate ways they learn and evolve. Think of it as a guided tour through the brains of AI, designed to give you that well-informed edge. Maybe with a few surprising facts and hopefully enough humor to keep you hooked.
What's truly compelling here, I think, is that to effectively navigate, manage, or even just, appreciate the profound impact of AI in our world, you first need a solid grasp of its fundamental architecture. It's kind of like trying to understand a complex machine without knowing what its gears or circuits actually do. And a key challenge we face is simply categorizing something as complex and rapidly evolving as artificial intelligence. Our deep dive today will provide that essential clarity, helping you grasp the underlying structure that makes these systems tick and gives them their, well, varied capabilities.
Okay, so let's peel back the first layer then. We're starting with the fundamental types of AI, exploring how they differ in their basic functionality and then their broader capabilities. You might actually be surprised by the diversity within that single term, AI.
Exactly. Our manual starts with the most rudimentary forms of AI and then progresses to the most advanced theoretical stages. And this progression isn't just historical, it helps us appreciate the journey of AI development and, precisely where current real-world capabilities actually sit versus future aspirations.
That makes a lot of sense. It's a good framework to think about it.
Yeah.
So where do we begin on this spectrum? What's first?
Okay, first up are reactive machines.
Reactive machines. Got it.
Yeah, kicking things off at the absolute ground floor, we have reactive machines. These are the earliest and most fundamental forms of AI. Their operational environment is strictly limited. They only respond to current stimuli without any memory of past experiences. And crucially, they can't learn or improve from those experiences over time. They just execute pre-programmed specific tasks with incredible efficiency and speed.
Right, like Deep Blue, the chess computer. That's the classic example our source highlights, isn't it? IBM's Deep Blue, the one that beat Garry Kasparov. It sought a board, analyzed moves, picked the best one based on programming, but it didn't, remember past games to learn or feel bad about a losing move.
Exactly. Or think about basic industrial robots on an assembly line. They weld or paint or assemble based on immediate sensor inputs without a cumulative understanding of the hundreds of welds they've already done.
So it's brilliant at one specific task, like a specialized supercomputer designed only for that one calculation.
Precisely. It can process immense amounts of immediate data and make complex decisions within its defined scope, but it doesn't build a knowledge base or learn from its own past actions. And here's a kind of counterintuitive insight. This simplicity is often their greatest strength.
Oh, really? How so?
Well, in highly predictable, high-speed environments, the overhead of memory or complex learning would actually slow things down. It would be a detriment, not a benefit. This shows us that intelligence isn't always about complexity. Sometimes it's about pure, unburdened efficiency.
That's a fascinating point about efficiency. So the lack of memory isn't always a bug. It can actually be a feature for certain tasks. Makes sense.
Right. So moving on from reactive,
Okay, stepping up the ladder, we arrive at limited memory AI, so this must be a bit smarter.
it represents a significant leap, yeah. Because its defining characteristic is the ability to recall past experiences, though only for a short, specific duration. This recent memory allows it to inform its current decisions and actions, making it much more dynamic and context-aware. But, and this is vital to grasp, it doesn't store permanent long-term memories or build a cumulative life story. Its memory is strictly short-term and tactical.
Okay, so what are some examples? Our source points to things we use every day, right?
Absolutely. Think of autonomous vehicles, self-driving cars. They remember recent traffic patterns, the location of other cars, obstacles in the immediate vicinity. all to navigate safely in real time.
Mm-hmm.
Virtual assistants like Siri or Alexa retain context from your ongoing conversation to provide more relevant responses, remembering your last few commands.
Got it.
And recommendation systems like on Netflix or Amazon use your recent viewing or purchase history to suggest new items you might like.
Right. So if reactive AI is that specialized calculator, limited memory AI is like a really intelligent short-term planner. It remembers the last few turns on your drive to figure out the next one, or your last few searches to suggest something relevant now.
Exactly. This introduction of even limited memory significantly expands AI capabilities, moving beyond static responses to truly dynamic, context-aware decision-making, which is absolutely crucial for many real-world applications where ongoing context is vital for effective operation.
Yeah, you need that context.
And what this also highlights is why data quality is so paramount. If that short-term memory is flawed, even temporarily,
Then the decisions are flawed too.
inevitably, yeah, potentially leading to critical errors in dynamic scenarios.
So it's about having enough memory to be useful in dynamic situations, but not so much that it's, I don't know, getting bogged down or trying to understand philosophy.
Precisely. It's optimized for the task.
Okay, so next up, theory of mind AI. Now this sounds like where things get really mind-bending. We're moving into more conceptual territory.
Definitely. This is an aspirational stage of AI development, still largely in the research phase, representing a monumental ambition. The ultimate goal here is to create machines capable of understanding nuanced human emotions, beliefs, intentions, and the intricate complexities of social dynamics.
Wow.
Yeah, this involves developing something akin to empathy, self-awareness, and the ability to interpret and respond to the subtle cues of human interaction. It's about much more than just processing words. It's about understanding the unspoken, the intent behind the words, and the unspoken social rules.
Okay, so are there any early examples? Our source mentions things like ChatGPT.
Right. Advanced language models like ChatGPT, for instance, can generate remarkably human-like text and engage in seemingly thoughtful and coherent conversations. Now, while they don't truly understand in a human sense, they can mimic that understanding very convincingly.
Mm-hmm.
Similarly, social robots like Pepper are designed with elements that attempt to read and respond to human emotions, though, still in a pre-rudimentary way compared to the full vision of theory of mind AI.
Okay, so imagine an AI therapist that could pick up on subtle vocal cues of distress.
Exactly. Or a truly intuitive customer service agent who can sense your frustration without you explicitly stating it.
Or maybe even a companion robot that genuinely understands and adapts to your mood throughout the day.
Right. If we connect this to the bigger picture, theory of mind AI represents a massive conceptual leap. It's shifting from purely functional or reactive tasks to attempting to grasp the complexities and subtleties of human interaction. And this naturally brings up a challenging question.
The ethical implications.
Well, yes, but also the practical and societal challenges. When AI aims to understand and respond to human emotions and social behavior, how do we ensure these systems integrate smoothly and predictably into our daily lives? How do we avoid creating unforeseen social dependencies or, major misunderstandings?
That's a huge leap for sure. And yeah, those challenges become very real very quickly.
Absolutely. And then the final stage on this functionality spectrum.
Self-aware AI. Okay, now we're really venturing into the deep end, aren't we? This is theoretical, speculative stuff.
Purely speculative at this point, yes. Self-aware AI refers to machines that would possess true consciousness, self-awareness, and sentience. This means they would operate with independent thought, desires, and subjective experiences, essentially mirroring human consciousness. They'd have an understanding of their own existence, their own agency, and potentially even their own internal states and motivations.
So this is HAL 9000 from 2001, a space odyssey, or data from Star Trek territory, stuff from sci-fi.
Precisely. Currently, this remains firmly in the realm of science fiction and philosophical debate, a distant future rather than a present reality. Those are the archetypes of what self-aware AI might ultimately represent.
So what does this all mean for us? I mean, talking about AI that knows it exists, has feelings, maybe even dreams. It pushes the boundaries of our understanding of intelligence itself.
It really does. And what's truly fascinating here is that while highly theoretical, maybe even centuries away, the very contemplation of self-aware AI forces humanity to deeply consider the nature of consciousness itself and our place in the universe and the profound societal and philosophical shifts that would occur if such a system ever came into being. It challenges our very definition of what constitutes an intelligent entity.
Yeah, fundamentally.
So the big question it raises is If AI ever achieved true self-awareness, how would we even begin to define its operational parameters? Or its place within our existing legal and social structures? It's a question that delves into entirely new territory.
Indeed. It's the ultimate thought experiment for AI, really.
Mm-hmm.
Okay, so that covers the spectrum based on functionality.
Hmm.
But you mentioned our source also categorizes AI by its capabilities. How does that differ?
Right. This categorization helps us understand what an AI is specifically built to do, from the highly specialized tools we use every day to those sci-fi dreams of superintelligence. It's less about how they think and more about what they accomplish practically.
Got it. Less about internal complexity, more about scope of action.
Exactly. And you'll notice that most of our practical, real-world examples of AI tend to fall into the first category here.
Okay, so what's first under capabilities?
Narrow artificial intelligence, or ANI.
ANI, also known as weak AIs, right?
Correct. ANI is specifically designed and trained for a single, very specific task. It excels at its designated function, but fundamentally cannot perform tasks outside its program scope. And it's crucial to understand that most, if not all, the AI applications we use and interact with daily are examples of ANI.
Like my smartphone's voice assistant, Siri or Google Assistant. It's great at setting reminders or telling me the weather, but it can't suddenly, I don't know, write a poem.
Exactly. Or image recognition software, identifying faces in photos, email spam filters, recommendation engines on Netflix or Amazon. These are all prime examples of ANI. They are highly skilled and incredibly useful for their singular purpose, but they can't decide to compose a symphony unless they're specifically programmed for that particular creative task. They're specialists, not generalists.
Right. Experts in one field.
And from a broader perspective, ANI is truly where the practical, tangible benefits of AI are currently realized across almost every industry. It's the workhorse of the AI world. However, as ANI systems become more sophisticated and pervasive, a critical question arises.
Which it is.
How do we manage the escalating complexity of these numerous single-purpose systems, especially when they start to interact and combine in unforeseen ways, creating potential vulnerabilities or dependencies within larger technical ecosystems?
That's a good point. It's not just about one AI in isolation, but how they all work together, or maybe sometimes against each other accidentally.
Precisely. The interactions can be complex.
Okay, so from narrow specialists, we move to artificial general intelligence, AGI.
Correct. AGI, also known as strong AI. Now, AGI refers to AI that would possess human-level cognitive abilities across a wide range of problems. It implies an AI that can understand, learn, and apply intelligence similarly to how a human does. It would have common sense, adaptability.
And the ability to transfer knowledge between different domains.
Yeah.
Like learning critical thinking and applying it to something totally new.
Exactly, just as we can. This is still a theoretical concept, though, and remains a significant long-term research goal for the AI community.
So no real examples exist yet.
No fully realized AGI systems, no. The concept envisions an AI that could, say, learn a new human language, then apply that to understand a complex scientific paper, and then use that understanding to design a novel experiment, all without explicit pre-programming for each specific task.
A truly versatile problem solver, the jack of all trades AI.
Right. But from a governance and risk perspective, AGI would introduce unprecedented complexities.
How so?
Well, think about unpredictable behavior, emergent properties, the sheer scope of its potential impact. Our current governance frameworks are largely built for systems with defined, limited functionalities.
Yeah, they expect predictability.
So a critical question comes to mind. Are our current governance and control frameworks even remotely equipped, conceptually or practically, to handle a system with human-level general intelligence and adaptability, let alone its potential for unforeseen impacts across society and the economy? It's a fundamental challenge.
It's a huge challenge to consider. And then beyond AGI, there's the final frontier, artificial superintelligence, ASI.
That's it. The ultimate theoretical stage of AI, where artificial intelligence would not just match but profoundly surpass human intelligence in all aspects. And that includes not only raw processing power and problem solving, but also creativity, social skills, emotional understanding, general wisdom, everything.
Wow.
ASI would be able to perform intellectual tasks far beyond human capability, leading to implications that are frankly difficult for us to even fully comprehend right now.
So this is purely speculative, stuff for philosophers and futurists.
Pretty much. It implies a level of intelligence that could perhaps solve humanity's greatest challenges: climate change, disease with ease, or, conversely,
Pose unprecedented challenges if its goals diverge from ours. The classic sci-fi scenario.
Exactly. For better or worse, it's the definition of a superintelligence. And if we connect this to the bigger picture, ASI represents an immense, potentially transformative and disruptive force for humanity. Its implications are so vast. Discussions around it often extend into areas like transhumanism and the very future of civilization itself. The sheer magnitude of its potential capabilities compels us to consider its implications now.
So what's the key question it raises for us now?
What fundamental safety and control mechanisms must we begin to establish and rigorously enforce now to guide research and development? How do we ensure that any path towards ASI prioritizes predictable operation and human oversight without unintended consequences? It's about building in guardrails before we even get close.
Right, planning ahead for something potentially monumental. Okay, that gives us a really solid map of the different types of AI. Where do we go next?
Well, now that we've grasped the types based on function and capability, let's zoom in on some of the core models that actually power them.
Okay. So if you've ever wondered how AI seems to magically create new things or predict the future, this next part is for you, right? We're peeking behind the curtain.
Exactly. Our source highlights two critical functional types, generative and predictive AI, and then delves into the foundational machine learning paradigms that often underpin them. It's like looking at the engines driving the car.
All right, let's start with the really buzzy one right now. Generative models. Gen AI.
Right, generative artificial intelligence. This is a truly transformative branch of AI that has the unique ability to create new and original content. And this content can range from incredibly realistic text and images to music, video, even functional computer code.
How do they do that? They don't just copy things.
No, they learn complex patterns and relationships from vast amounts of their training data and then use that deep understanding to produce novel outputs that didn't exist before. They don't just replicate or combine existing pieces, they synthesize and create truly original works, though always based on patterns observed in their training data.
Okay. And the source mentions GANs, generative adversarial networks.
Yeah, GANs are a prime example. They work through a fascinating competitive process. You have two neural networks, a generator that creates new content, like an image,
Okay.
and a discriminator that tries to identify whether the content is real from the training data or fake, created by the generator.
So they compete.
Exactly. This adversarial process drives the generator to produce increasingly realistic and high-quality outputs because it's constantly trying to fool the discriminator.
That's clever. Like an art forger trying to fool an expert.
Kinda, yeah. Think of how deep fakes are created, or highly realistic synthetic images, or those text-to-image generators you see online.
Right, those are everywhere now.
And large language models, LLMs, also fall into this category. They generate human-like text for everything from creative writing to answering complex questions and drafting customer service responses.
It's like having an infinite artist, writer, or musician at your fingertips, capable of producing original works.
It really is. And what's truly remarkable here is the immense creative potential unlocked by these generative models. They're genuinely reshaping industries from entertainment to product design. But, and this is a big but, with that power comes complex new questions.
Like copyright. If an AI creates something amazing, who owns it?
Exactly. If AI can create content indistinguishable from human work, how do we establish clear ownership and intellectual property rights? And what about the sheer proliferation of synthetic media? How do we manage the volume and authenticity of all this new content in a world where anyone can generate realistic-looking text or images? It challenges our very understanding of originality and provenance.
It definitely blurs those lines, doesn't it?
Yeah.
Makes you question what's real and what's generated sometimes.
Mm-hmm.
Okay, so that's generative AI, the creators. What about the other type? Predictive models.
Right. If generative AI creates predictive AI forecasts, these models are designed to analyze historical data with the goal of identifying trends, forecasting future outcomes, or classifying new data points into predefined categories. They're widely employed for decision-making across various domains by inferring complex relationships within existing data.
So, like financial forecasting, predicting market trends.
That's a key example. Or sophisticated fraud detection systems that flag suspicious transactions based on past patterns of fraudulent activity. Or customer behavior analysis models that predict purchasing habits, allowing businesses to tailor marketing strategies. These models are crucial tools for businesses making informed strategic and operational decisions, optimizing processes and resources with a data-driven outlook.
It's like having a crystal ball, but one trained on tons of past data.
A data-driven crystal ball, yeah. And from a broader perspective, predictive models are truly at the heart of many operational and strategic business applications today. They optimize everything from inventory management to risk assessment. But the crucial aspect here isn't just the existence of the prediction, it's the accuracy, robustness, and consistency of these predictions.
Consistency matters,
Yeah,
right? Not just being right on average.
absolutely. So this brings up a critical question. How can organizations ensure that their predictive models are not only statistically accurate, but also robust and consistent across different data segments, especially when their forecasts or classifications could directly impact individuals, like in loan approvals, insurance decisions, or even hiring processes? You want consistent, fair outcomes, not just average accuracy.
Consistency is key, yeah, especially when real decisions affecting people are on the line. Okay, so we have generative and predictive models. What about the underlying learning mechanisms? Machine learning.
Exactly. Now, this is where the real learning happens. Machine learning, or ML, is a fundamental subcategory of AI. It enables systems to learn from data without being explicitly programmed for every single possible scenario.
So they teach themselves, in a way.
Kind of. ML algorithms identify patterns, build models based on those patterns, and then use these models to make decisions or predictions. It's about adaptive intelligence systems improving their performance over time with more data and experience.
That adaptability sounds powerful.
It is. Unlike traditional programming, where you explicitly tell the computer what to do for every specific case, ML models figure out the rules and relationships themselves directly from the data. This allows them to handle complex, evolving problems that are difficult or impossible to hard code manually. So, a critical question for any organization diving into ML is this. Given ML's reliance on data as its primary learning source.
And you need good data, right?
Yeah.
Garbage in, garbage out.
Precisely. How do we ensure the input data is consistently of high quality, relevant, and representative of the intended operational environment? Because ultimately, the model can only be as good as the data it learns from.
That makes perfect sense.
Yeah.
Okay, so let's dive into the 3 core ways these ML models learn. What's the first one?
Supervised learning.
Supervise. Okay, like having a teacher.
Exactly. This is one of the most common ML techniques where models learn from what we call a labeled data set. This means the input data is directly paired with the correct output, essentially acting as a teacher for the algorithm. The model learns by identifying patterns and relationships between these known inputs and outputs, and then applies this learned knowledge to new, unlabeled data to make accurate predictions.
And our source mentions 2 main types within supervised learning.
Right. Regression, which predicts continuous numerical values like a house price,
Okay.
and classification, which predicts discrete categories or labels like spam or not spam.
Got it. Can you give a concrete example?
Sure. The classic one is image classification. You feed an algorithm thousands of images of, say, cats and dogs, with each image clearly labeled cat or dog. The algorithm learns the features that distinguish cats from dogs. Eventually, when you show it a new, unlabeled picture, it can accurately identify whether it's a cat or a dog.
Ah, okay. So it learns from examples with answers provided.
Exactly. Or email spam detection, labeling emails as spam or not spam, or predicting house prices based on labeled features like size and location. It's a very direct form of instruction with clear feedback.
Right, so it's powerful if you have good labeled data.
Incredibly powerful, yes. It's the backbone of many practical AI applications. However, its performance is directly tied to the quality and representativeness of that training data.
And that leads to a challenge.
It does. What happens when the real-world data the model encounters during operation deviates significantly from the data it was originally trained on? Or if the labeling process itself was incomplete or inconsistent? The model's effectiveness can quickly degrade in such scenarios, which is something many organizations overlook post-deployment.
It's like teaching a student only from old textbooks and then expecting them to ace a test on current events. Doesn't quite work.
That's a great analogy.
Okay, so if supervised learning needs labeled data, what's the alternative? Unsupervised learning.
Correct. Building on that, we have unsupervised learning. Unlike supervised learning, this technique deals with unlabeled data. The core goal here is for the algorithms to discover hidden patterns, underlying structures, or previously unknown relationships within the data entirely on their own without any prior knowledge of the desired output.
So no teacher this time.
No teacher. It's primarily about exploratory data analysis and finding inherent organization within a data set. The AI is essentially tasked with making sense of a large, unstructured pile of information, like a data detective.
Interesting. What kinds of techniques does it use? Our source mentions a few.
Yes, several key types. One is clustering. This groups similar data points together based on their inherent characteristics.
Like sorting things?
Exactly. K-means clustering is a classic example, used for things like customer segmentation, grouping customers with similar purchasing habits to tailor advertising, or even in science, like human gene mapping to identify related genes. It's like sorting a pile of diverse objects into categories the AI finds for you.
Okay, clustering. What else?
Another type is association rules. This identifies relationships between variables in large data sets.
Ah, like the customers who bought X also bought Y thing.
That's the famous example, often called market basket analysis. It's how supermarkets decide where to place items to maximize sales.
Clever. Okay, and the third one mentioned.
Dimensionality reduction. This transforms high-dimensional data with lots of features or variables into a lower dimensional representation while retaining its essential features.
Why would you want to do that?
It simplifies complex datasets. Principal component analysis, or PCA, is a common example. It can simplify images for easier analysis without losing crucial information, or reduce the number of variables in a dataset to make it more manageable for other algorithms.
Got it. So unsupervised learning is really about discovery, finding hidden patterns.
Precisely. What's truly remarkable here is its unique ability to uncover hidden insights and unknown relationships in vast, complex datasets that humans might completely miss. It's particularly useful when labeled data is scarce, expensive, or simply impossible to predefine.
But there's a challenge too, right? If there's no right answer.
Exactly.
Then,
How do we effectively interpret, validate, and ensure the reliability of the patterns and groupings found by unsupervised models, especially when there's no human ground truth to compare against? It can sometimes make it harder to trust or fully explain the outcomes. You find a pattern, but you might not know why it's there or if it's truly meaningful.
so great for discovery, but maybe leaves you with more questions about why those patterns exist. Okay, that makes sense. What's the third learning paradigm?
Reinforcement learning, or RL.
Reinforcement learning. Okay, this sounds different again. More dynamic.
Very dynamic and adaptive, yes.
Yeah.
RL focuses on how an intelligent agent learns to make optimal decisions by interacting with an environment. The agent performs actions, receives rewards for desirable outcomes and penalties for undesirable ones, and iteratively adjusts its strategy to maximize its cumulative reward over time.
Ah, like learning through trial and error, like teaching a dog tricks with treats.
That's a perfect analogy. It's essentially learning through a continuous process of trial and error. Think of learning to ride a bike. You try, you fall, penalty, you adjust, you succeed, reward.
Okay, what are some AI examples? The source mentions AlphaGo.
Right. Iconic examples include AI mastering complex games like DeepMind's AlphaGo, which beat the world champion at Go. It learned through countless simulated games, optimizing its strategy by being rewarded for wins. Other real-world applications include AI systems controlling robotic path planning, where a robot learns the most efficient way to navigate an obstacle course, and enhanced autonomous driving systems, where the AI learns the optimal way to drive safely and efficiently by being rewarded for good driving decisions and penalized for bad ones.
So the AI gets rewards for good behavior and learns through experience to find the best way to achieve its goal, rather than being explicitly programmed for every single action.
You've nailed the concept, and from a broader perspective, RL is incredibly powerful for dynamic and complex environments where the optimal strategy isn't obvious upfront or changes frequently. It allows for highly adaptive and intelligent behavior.
But I sense a however coming.
Well, yes, it brings up a fascinating challenge. How do we design the reward system effectively and comprehensively? How do we ensure the AI learns only desired behaviors and doesn't exploit unforeseen loopholes in its objective function just to maximize its reward?
Ah, the AI finding a clever, unintended way to get the treat.
Sometimes, yeah. An AI can find a highly unexpected but technically effective way to get rewards that we didn't intend, leading to undesirable overall behavior. Defining that reward function correctly is critical.
That's a classic sci-fi trope right there, the
Good.
AI that's too good at gaming the system. Okay, so we've covered the learning paradigms. Where does that take us next? Into the architecture.
Exactly. We've explored the broad categories of AI and the distinct learning styles. Now let's peer deeper into the actual brain of many advanced AI systems, neural networks.
Neural networks. These draw inspiration from our own biological brains, right?
Profound inspiration, yes. And we'll also look at the specific algorithms that make them tick and guide their learning processes. This is where the magic, or rather, the intricate engineering, truly happens.
All right, let's unpack neural networks, NNs.
Okay, so neural networks are complex collections of algorithms designed to mimic the fundamental structure and function of the human brain. They are incredibly powerful at identifying intricate patterns, classifying data, and making predictions. They consist of interconnected layers, an input layer where the raw data first enters,
All right.
one or more hidden layers where the bulk of computation, pattern recognition, and learning truly occurs.
The processing part.
Right. And an output layer which produces the final prediction, classification, or result. And our source emphasizes that deep learning, DL, is a highly influential subcategory of ML that specifically refers to neural networks with 3 or more hidden layers. This multi-layered or deep structure allows for incredibly complex and abstract pattern recognition.
Okay, so deep just means more layers in the middle.
Essentially, yes. And those extra layers allow it to learn hierarchical features, simple features in early layers, combining into more complex ones in deeper layers.
Got it. Our source has diagrams, figures 1.5 and 1.7, showing this flow.
Yes, they visually represent how data flows through these layers, transforming and refining as it progresses to generate better insights.
So imagine a vast network of interconnected neurons processing information in stages or layers. That's a neural network. And many layers make it deep learning.
Exactly. And what's truly remarkable here is the sheer power of deep learning to extract incredibly complex and abstract features from vast amounts of unstructured data like images, audio, raw text, which traditional methods often struggle with. This capability has driven profound breakthroughs in fields like natural language processing, where machines can now generate coherent text and computer vision, enabling self-driving cars to see their environment.
But there's that black box problem, isn't there? The complexity makes them hard to understand.
That's the trade-off. Their very complexity means they can be challenging to understand internally. So a crucial question arises. Given their inherent complexity and often opaque nature, how do we gain sufficient insight into their internal workings to ensure reliability and diagnose issues? It's a significant engineering challenge.
That's the million-dollar question, isn't it? How do we trust something we can't fully see inside? For listeners, what's the most common misconception about these networks? Are they all the same?
That's a great point. A common misconception is that all neural networks are the same, or just one big amorphous blob of processing. But as our source highlights, that's far from the truth. Not all neural networks are built the same way. They have different architectures optimized for different types of tasks.
Okay, so what are some key types?
Well, the source highlights 3 common ones. First, the feed-forward neural network, FNN.
Feed forward. Sounds straightforward.
It is. It's the simplest type, where information flows in only one direction. Input through hidden layers to output, new cycles or loops, a linear progression.
And what's it used for?
Commonly used in tasks like email filtering, basic image recognition for simple classifications, and general classification problems where the output is directly derived from the input. Simple structure for simpler tasks.
Okay, what's next?
Recurrent neural networks, RNNs. These are designed specifically for sequential data.
Like text or speech, where order matters.
Exactly. RNNs have internal loops or feedback connections that allow information to persist. This means they can remember past inputs and use that context for current and future predictions.
Ah, so they have a kind of memory.
A short-term memory, yes. This makes them crucial for language translation, understanding sentence flow, speech recognition systems, processing spoken words in sequence, and generating text, where context from previous words is vital.
But you mentioned a challenge, remembering long sequences.
Yes, that can be an issue with basic RNNs. The signal or memory can fade over very long sequences. More advanced versions address this, but it's a known limitation.
Got it. And the third type?
Convolutional neural networks, CNNs. These are highly specialized for processing grid-like data, most notably images.
Images. Okay, how do they work differently?
CNNs use special convolutional layers that automatically detect patterns, features, and objects within images, much like how our visual cortex processes visual information. They're incredibly efficient at spotting visual hierarchies, edges, shapes, textures, objects.
So they're tailored for vision tasks.
Primarily. Widely used in photo tagging on social media, identifying anomalies in medical imaging like X-rays or MRIs, object detection in autonomous vehicles, spotting pedestrians, cars, signs, and complex video analysis.
Okay, so different problems really do call for different brain structures. Simple flow for FNNs, memory loops for RNNs, pattern detectors for CNNs. It's about adapting the architecture.
Precisely. The choice of neural network architecture is absolutely crucial for a model's performance and efficiency. Selecting the wrong architecture can severely limit capabilities or make it incredibly inefficient. Understanding these fundamental types helps auditors, developers, anyone really, evaluate the suitability and potential limitations of an AI solution. And it leads to a deeper consideration. How does the inherent structural design influence specific limitations or susceptibilities? For example, CNNs excel at images, but you wouldn't typically use them for text analysis. That's where RNNs shine.
That distinction is really helpful. It's not just about a neural network, but the right kind of neural network for the job. Okay, so NNs are the architecture. What about the algorithms inside them? The recipes.
Right. So if NNs are the brains, algorithms are the recipes the brain uses. At their core, algorithms are step-by-step instructions or sets of rules an AI system follows to solve a problem or perform a task. They're the foundational, programmatic understanding of ML. And critically, their performance is often optimized by adjusting hyperparameters.
Hyperparameters. Those are the settings that control the learning process itself, right? Like the learning speed or the complexity.
Exactly, like the learning rate, how fast the model learns, or the depth of a decision tree influencing its complexity.
So algorithms are the instructions, hyperparameters are like fine-tuning those recipes, adding a pinch more salt, reducing the heat to get the best outcome for that specific data and task. Sounds like a delicate balance.
It is. And what's truly fascinating here is that while algorithms dictate the how of learning, what they actually learn and how well they learn is heavily dependent on the data quality, data representation, and, crucially, the correct tuning of those hyperparameters. Suboptimal hyperparameters can significantly hinder performance, leading to poor results even with excellent data.
So getting those settings right is key.
Absolutely. It highlights a key challenge. How do organizations ensure diligent expert oversight of both algorithm selection and hyperparameter tuning? It requires deep expertise and continuous iteration.
Makes sense. Our source provides a quick tour of some common algorithms,
Right.
referencing figures 1.8, 1.8. It looks like a big toolkit.
It is a vast toolkit. Let's touch on the main classes. First, supervised learning algorithms.
Okay.
We have linear regression, predicts a continuous value by finding a linear relationship. Think predicting house prices based on square footage. Straightforward, but assumes linearity.
Right.
Logistic regression predicts the probability of a category, often binary, yes, no, used for classification. Example, email spam filtering.
Got it.
Tree-based models, like decision trees or random forests. They use a tree structure of decisions, highly interpretable. Example, credit risk assessment. They're powerful for complex, nonlinear stuff and support vector machines, SVMs, primarily for classification. They find an optimal hyperplane to separate data points, effective even with limited data. Example, image classification.
Okay, that's good set for supervised. What about unsupervised learning algorithms?
We touched on some concepts. Here are algorithms. K means clustering. Divides data into a predefined number, K, of clusters based on similarity. Example, customer marketing segmentation. Simple and efficient.
Right, finding groups.
Hierarchical clustering builds a hierarchy of clusters, either bottom-up or top-down. Example, human gene mapping, great for visualizing nested relationships.
Okay.
And principal component analysis, PCA, a dimensionality reduction technique, transforms complex data into fewer components capturing most variance. Example, image compression, simplifying data.
Makes sense. And finally, reinforcement learning algorithms.
Yep. Q-learning, a model-free algorithm where an agent learns an optimal policy by finding the best action per state to maximize future rewards. Example, robotic path planning.
Learning values of actions.
Deep Q networks, DQN, extends Q-learning using deep neural networks for complex state spaces. Learns from raw inputs. Example, enhanced autonomous driving.
Using deep learning for RL.
And policy-based methods. These directly learn a policy, a mapping from states to actions without needing value functions. Example, robotic arm control can be better for continuous actions.
Yeah, that really shows the incredible versatility. There's a specific recipe or algorithm for almost any task imaginable, whether it's predicting, categorizing, or robot learning.
It's a vast and ever-growing toolkit. And from a broader perspective, the choice of algorithm heavily influences the model's strengths, weaknesses, and suitability. Auditors, developers, anyone involved needs to understand these choices to assess risks like inaccuracy or lack of robustness. So a key consideration is, How do we choose the right algorithm for the specific problem, and what are the crucial trade-offs involved? It's not just picking the most powerful, but the best fit.
So it's about matching the right tool to the job, not just using a hammer for everything. Makes
Yeah.
perfect sense. Now, there's one more crucial thing mentioned here. Overfitting. Sounds like a pitfall.
It's a critical concept and a common challenge, yes. Overfitting.
So what does this mean? Is it like learning too much?
Exactly. Overfitting occurs when an AI model learns the training data too well. It essentially memorizes it, including all the noise, errors, and outliers present in that specific data set. As a result, while it performs exceptionally well on the data it was trained on, its performance degrades significantly when presented with new, unseen data from the real world. The model has memorized, rather than truly understood or generalized, the underlying patterns.
Oh, the source has figure 1.10 showing this visually, right? Like a line wiggling to hit every single training point.
Precisely. You might see an overfitted model drawing a highly complex, jagged line that perfectly traces every training data point, but that complex line completely fails to accurately predict new, slightly different data points.
It's like studying for a test by memorizing every single question and answer from old exams, including the typos. You ace the old test.
But fail miserably on the actual exam with new questions testing the concepts. That's a perfect analogy.
So it gives a false sense of security during testing.
It can, yes. Overfitting highlights that fundamental challenge, balancing model complexity with its ability to generalize to new data. This leads to a critical question for organizations. How can we implement robust validation techniques? Things like using separate validation datasets, cross-validation, and establish independent reviews to diligently detect and mitigate overfitting before deploying models in critical applications.
It's about ensuring the model performs well not just in the lab, but in the wild. Building a model that can think for itself, not just parrot back.
Exactly. Robustness and generalization are key.
Okay, this has been incredibly insightful on the models and algorithms. But these systems don't just appear, right? They have a whole life cycle.
That's the next crucial piece. We've built up a strong understanding of AI types, models, algorithms. But an AI system isn't static code. It has a whole life cycle, from initial idea to eventual retirement. It's a continuous dynamic process. Let's trace that journey.
All right, the AI life cycle. Let's dive in.
Okay, so the AI life cycle refers to the complete process: creating, implementing, operating, and ultimately decommissioning AI solutions. Our source emphasizes that while it shares similarities with a traditional system development lifecycle, SDLC,
Like for regular software.
right, but AI introduces unique considerations and heightened risks, things related to data quality, model interpretability, fairness, ethics, and the sheer iterative nature of AI development. These risks can emerge and evolve at any stage.
Okay, and the source has a diagram, figure 1.11, the OECD AI life cycle. What are the main phases?
Yes, it visually represents the key phases: plan and design, collect and process data, build and adapt models, test, evaluate and validate, operate and monitor, and finally, retire, decommission.
It looks like a continuous loop, almost.
It often is. The flow underscores the iterative and interconnected nature. Insights from later stages can feed back into earlier ones for continuous improvement.
So, like any product, AI has a beginning, middle, and end. But its journey is more dynamic, with each stage impacting the next.
Precisely. And what's truly fascinating here is that AI's iterative nature and heavy dependence on data mean new risks can emerge, or existing ones manifest differently at virtually any stage. An auditor, for example, needs to consider risks not just during development, but also data collection, ongoing training, continuous operation. It requires a much broader risk assessment approach.
So the key question is about oversight across the whole cycle.
Exactly. How do organizations establish effective governance and continuous oversight mechanisms that span the entire AI lifecycle, ensuring ongoing vigilance and adaptability, rather than just focusing on a one-time check at deployment?
It's a living system that needs constant attention, not just a build and forget thing.
Absolutely.
Okay, let's break down each of these critical stages. First up, planning and design.
All right, the foundational phase. This involves clearly defining the AI system's objectives, thoroughly understanding requirements, outlining its architecture, and crucially, accountability frameworks must be integrated from the very outset. It's not just about what the AI will do, but how it should do it responsibly, aligning with organizational values and societal expectations.
This is the blueprint phase, deciding what the AI achieves, who it serves, and how to make sure it's responsible and ethical from day one, building the functional and ethical foundations.
Precisely. Robust planning and design are absolutely critical for mitigating significant risks before they even get coded in. A well-defined mission, clear objectives, early integration of ethical principles, these contribute immensely to a trustworthy system. Without this upfront work, you risk building something technically functional but maybe misaligned with operational realities or intended purposes.
So the fundamental question here is about embedding those considerations early.
Yes. What specific mechanisms are in place during this early planning stage to ensure all requirements, potential operational challenges, and ethical considerations are thoroughly embedded, ensuring a robust and well-aligned system right from the start?
It sounds like getting it right here prevents a lot of headaches down the road.
It really does.
Okay, phase two, collect and process data. This sounds crucial for AI.
Extremely crucial. This stage involves systematically gathering, cleaning, and transforming the vast amounts of data needed to train, test, and validate the model. Our source notes this is often the most time-consuming and resource-intensive phase in the whole life
I
cycle.
believe it. Data wrangling.
Exactly. And the quality, relevance, and representativeness of this data are paramount. If the data is flawed, incomplete, biased, or irrelevant, it introduces significant errors and risks that will inevitably propagate into the AI's behavior.
This is where the AI gets its food, right? If the food is bad, incomplete, biased, irrelevant, the AI won't learn correctly. Garbage in, garbage out.
That's the classic phrase, and it's absolutely true here. The quality of this raw material directly impacts the intelligence and reliability of the final product. Data is the lifeblood of AI models. The choices made in collection and processing directly determine performance, fairness, generalizability. This stage is particularly prone to introducing or amplifying biases if not handled with extreme care.
So the challenge is maintaining data integrity.
Right. How can organizations implement robust data governance and quality assurance practices? How do they ensure the training data is consistently representative, accurate, and free from biases that could lead to discriminatory or unfair outcomes? It's a continuous challenge.
A constant effort to keep that data clean and relevant. Okay, next stage. Build and/or adapt models. This is the training part.
This is where the actual AI model comes to life, yes. The chosen algorithms are selected or developed, and the model is trained using that meticulously processed data. It involves iteratively adjusting parameters, refining performance, optimizing learning. Our source emphasizes the vital role of human interpretability and continuous human oversight throughout this.
So it's not just letting the machine run wild.
Ideally not. It's about guiding the learning, ensuring the model behaves as expected, and aligns with objectives.
This is the training gym for the AI. Raw data transforms into something intelligent, guided by human experts. It's iterative train, evaluate, fine-tune.
Exactly. And from a broader perspective, model building is where learning truly takes shape, translating data into intelligence. Understanding how models arrive at predictions, identifying key variables, ensuring human oversight, these are paramount for a trustworthy solution, especially with complex black box models.
Which leads to that trade-off again. Accuracy versus explainability.
Yes. How do organizations effectively balance the imperative for high accuracy and performance with the equally critical need for understanding why a decision was made and the ability for humans to intervene or correct it? It's a constant balancing act.
It's all about finding that sweet spot between a model that works well and one you can understand and trust.
Precisely.
Okay, stage 4. Test, evaluate, verify, and validate. This sounds like quality control.
It is a truly crucial quality assurance phase. The model undergoes rigorous, multifaceted testing. We're checking accuracy, overall performance, reliability, and compliance with requirements and standards. It's not just, does it work, but does it work correctly, fairly, and robustly?
And the source mentions specific tests. Metrics like F1 score, precision, recall. Comparing actual versus expected outcomes.
Yes, all of that. Plus, specifically testing for bias and fairness across different groups and robustness against different kinds of inputs.
This is where we kick the tires, run diagnostics, make sure it works correctly and robustly under different conditions before deployment, because the stakes can be high once it's live.
Absolutely. And what's truly remarkable here is the need for diverse, sophisticated testing techniques. Simple performance metrics alone aren't enough. We must verify performance across various scenarios, ensure predictable and safe behavior even in unusual edge cases. This goes significantly beyond traditional software testing.
So the key question is about designing comprehensive tests.
Right. How can organizations design testing protocols that go beyond traditional metrics to truly assess an AI's behavior in edge cases, with varying data inputs, ensuring robust performance across all expected scenarios before it impacts real-world operations?
So not just testing the main road, but the bumpy back roads and weird detours too.
Exactly. You need to anticipate the unexpected.
Okay, next up, operate and monitor. The AI is live.
It's live, but the work isn't done. Once deployed, the AI solution requires continuous operation and diligent monitoring of its performance, outputs, and real-world impacts. Ongoing vigilance is essential to detect any performance degradation, data drift.
Data drift, what's that again?
That's when the relationship between the input data and the output changes over time in the real world, making the trained model less accurate because the world it was trained on is no longer the world it's operating in.
Ah, okay, so you need to watch for that. And anomalies or unexpected behaviors.
Exactly, due to changing real-world conditions or data inputs. Our source stresses the importance of robust feedback loops and clear, measurable performance metrics.
So the AI is in action, but now it's about continuously watching it, making sure it stays on track, performs as expected, doesn't go rogue, like nurturing a living system.
That's a good way to put it. Continuous monitoring is vital because AI models aren't static. They can degrade over time. This needs robust feedback loops and clear metrics to ensure ongoing reliability and prevent unforeseen failures.
So the challenge is being proactive, detecting issues quickly.
Yes. What mechanisms are in place to quickly detect and effectively respond to unforeseen performance degradation or operational anomalies, especially in autonomous systems where a slight degradation could have significant consequences? It's about being proactive, not just reactive.
Constant vigilance is the name of the game. Okay, the final stage, retire, decommission, the end of the line.
The final phase, yes. This involves systematically planning for the end of life of an AI system. It includes securely archiving relevant data, properly disposing of the models and their components, and ensuring all regulatory and compliance requirements for data retention and intellectual property are met. This step is crucial for maintaining data security, preventing breaches from old models, and ensuring overall system integrity.
Even AI systems eventually retire. But it's not just flipping a switch. There's a careful, secure process, especially with all the sensitive data and valuable IP involved, like a proper send-off.
Exactly. And what's truly fascinating here is that decommissioning is often overlooked, but is critically important for comprehensive data security, regulatory compliance, and responsible AI governance. Improper archival or disposal could lead to data leaks or misuse of IP from old models. Proper procedures ensure data is protected and accountability is maintained.
So the final question is about handling that end of life securely.
Right. How do organizations ensure that all data, models, and IP associated with a retired AI system are securely handled, permanently deleted where required, and fully accounted for according to regulations and internal policies? This phase needs just as much diligence as the others.
It sounds like just as much care needs to go into turning it off as turning it on. A full circle.
A complete life cycle, yes.
Wow, what an incredible deep dive today. We've really pulled back the curtain on the fundamental workings of AI. From the basic distinctions between reactive and self-aware AI, through the nuances of supervised, unsupervised, and reinforcement learning, and then tracing that entire comprehensive journey of an AI model through its life cycle, planning to retirement. It's clear that understanding AI is much more intricate and fascinating than just knowing what it does on the surface.
Indeed, we've seen how each component, from the initial choice of algorithm and neural network architecture to the meticulous management of the AI's life cycle, profoundly contributes to its overall effectiveness, fairness, and trustworthiness. A deep understanding of these fundamentals is absolutely essential, not just for AI auditors, but really for anyone who wishes to navigate, develop, or simply comprehend the rapidly expanding role of AI in our world.
So as AI models become increasingly complex, capable, and integrated deeper into our lives, having this foundational knowledge makes you truly well-informed. And it leaves us with this thought. As AI continues to evolve, perhaps even learning from its own experiences in ways we haven't fully grasped yet, how can we as humans ensure we maintain sufficient understanding and control over these powerful systems? And maybe more personally, what new critical thinking skills will you need to continually adapt and thrive in this increasingly intelligent future? Thank you for joining us on this enlightening deep dive into the brains of AI. Until next time, keep exploring.